How's it going, class? This is going to be our ninth lecture for the course. This is going to be on chapter 7. So, like I said, we're kind of jumping around a little bit. We'll be jumping back to chapter 7 here to talk about training for weight loss um, and caloric restriction. So, today we're going to go through a few different things. We're going to talk about high protein diets. We're going to talk about high carbohydrate diets. We're going to talk about what our total energy expenditure is, what RMR is. A lot of things that are really important for you if you are trying to put some sort of patient or individual through weight loss, as well as going to be useful information for yourself. A lot of what I have done, a lot of what um, exercise modalities and nutrition interventions that I've done the last couple of years have come a lot from recent research and a lot from individual research that's been published within different journals that tells us what our most recent level of knowledge is for certain things, as well as I'll talk a little bit about my own weight loss journey over the last year. I wouldn't really call it a weight loss journey. I would just call it more of a weight loss experiment that I performed on myself. Again, I'm not talking about myself too much, but it's a first-hand encounter with this type of literature. And I'll give you my thoughts as well as a lot of the more recent systematic review thoughts on these procedures. So we'll get going here. So training for weight loss. So a few different definitions. So our energy, our kilocalories, our food calories are things that we're going to be talking about a lot today. Energy intake. So just what it sounds like, this is the number of kilocalories or food calories that you consume. And remember when I say kilocalories or food calories, a food calorie that you see on your box of, let's say, Reese's Puffs or Lucky Charms or whatever it might be, or you see on the outside of your ice cream container, that is technically a kilocalorie. So a kilocalorie is one food calorie. It's just easier to write 220 calories per serving than easier it is to write 220,000, as well as just easier to understand. And then energy expenditure, energy output. So this is the amount of kilocalories or the amount of calories, I'm going to call them from now on, that you use. So this is the amount of energy that your body is requiring to do whatever you are doing during that time period. So how many calories you burn a day, how many calories you burn an hour, whatever that may be. Energy balance is the availability, the difference between energy intake and energy expenditure. So you'll hear me say energy deficit a lot, or caloric deficit a lot. So this is consume less energy than you burn, or a surplus is consume more energy than you burn. So as you're going to find out, everything having to do with weight loss has to do with energy deficit or energy surplus. If you are eating or you are intaking more energy than you are burning, you are going to store that energy predominantly as fats. And if you burn more energy than you are taking in, you are going to burn predominantly fats, right? That fat is the storage of energy within the body for the most part. Energy in the body. So we use energy to fuel basic vital functions, resting metabolic rate. We use it to fuel physical activity. So any movement that you do, exercise or non-exercise related, just raising your hands above your head, that took ATP to move those muscles, and therefore it utilized energy. Breaking down food just in general. So the thermic effect of food. So that is essentially the amount of calories or the amount of energy it takes to just break down your food. So you need to put effort into breaking down and catabolizing the food that you intake. So that is also going to require energy. And depending on what food you're intaking is going to change the amount of energy it requires to break down that food. So homeostasis, so 50% of the food is, or 50% of your energy is lost as heat. So part of the breakdown of food and part of the effect of different biological processes within the body is the production of heat, which allows us to stay in homeostasis. And so a big portion of the insufficiency or the ineffectiveness of the way that our body metabolizes food, or the way that really anything in nature does anything, is that a lot of it is lost as heat. You think about it like a light bulb. What is the purpose of a light bulb? A light bulb, the purpose is just to have electricity flow through the filament and to produce lights. But if you've ever felt an old light bulb, they get very, very hot. And even newer light bulbs now, halogens, LEDs, they still release some heat to a certain degree. And that's just energy lost. You're not using that heat realistically for anything. And especially down in Florida, you don't want that at all because you're trying to cool your house. And if all the lights in your house are heat in your house, that's the opposite of what you want. And so for a lot of energetic processes in all of chemistry, and specifically within the body, you lose a lot of the energy that you are looking for through heat. So we're looking at resting metabolic rate, or RMR. So this is 60 to 75% of your daily energy expenditure. So this is the amount of energy that your body requires to be at rest. The energy used for basic life functions, is should add at rest. So BMR, basal metabolic rate, is essentially the amount of energy that your body needs to maintain its living state, so to stay alive. But RMR is more specific to you being at rest, which is more conducive to you actually being alive, because BMR will be in a sort of coma state. While RMR, excuse me, is going to have to do a lot more with your actual life. So if you are just laying around every day, or you're sitting in a stable position and you are resting, RMR is going to be more accurate to that. And so that is highly individual and highly variable between different people. So the factors that can lead to it, the most important one is lean body tissue. And so when we talk about strength training, we talk about aerobic training, there's a lot more evidence now leading to the efficacy of strength training for weight loss rather than just aerobic training. And we'll probably get into that a little bit more in the lecture. But the biggest reason why is because strength training leads to increases, or hypertrophy training leads to increases in lean body tissue. Meanwhile, aerobic training mostly does not. And so while aerobic training can lead to greater caloric deficit in that day or in that exercise bout, hypertrophy and strength training will lead to greater increases in lean body tissue, and over time will raise your RMR and therefore may be more conducive for weight loss. So other factors that affect RMR, age, as we're going to find with age, RMR decreases. High caloric deficit will affect RMR, increased surface area. So with increased surface area, if you think about this, if you have more surface area, that means you are losing more heat. So in order to maintain optimal body temperature, you need to go through a higher state of metabolism. So you need to be burning more energy to maintain that body heat, because you are losing more body heat, and therefore you're going to have increased RMR. That's when we look at ancient populations. If you look at like the Cro-Magnon that lived on the African continents, they were very, very long and slender because they were in a very hot environment. So they had high body surface area because they didn't need to work to hold on the body heat because they were surrounded by high temperatures. Meanwhile, if you look at the Neanderthals that lived in the northern regions of some of the continents, they were very, very short and stout, as well as you look at even some Siberian and northern Russian populations, the tribes that live there, they are very short and stout because they live in a very cold environment. And therefore, being shorter and more round leads to lower surface area, which means they can more easily retain the heat, and therefore they are going to feel more comfortable and be less likely to freeze to death in the cold temperatures. High body temperature, if you have a naturally higher body temperature, so everything in the world, or everything in the body is on a continuum. We know that the average body temperature is 98.6 degrees, but some people's body temperature is 99.1. Some people's is 98.1. And so if your body functions the most optimally at 99.1 or 99.3, whatever it might be, you have an increased body temperature compared to the rest of the population. And therefore, in order to maintain that, in order to maintain the optimal levels of enzyme activity and overall biologic activity within the body, you need to have higher metabolism in order to maintain that body temperature. Hormones, so we'll find through pregnancy, testosterone, estrogen, cortisol, those things all affect your RMR. Menstrual cycle, we'll talk about that in a little bit as well. Hyperthyroidism, and then stress or cortisol. So here we're looking at the correlations between RMR and free fat mass, or fat-free mass. So as you can see here on the left graphs, as you increase your fat-free mass or your lean mass, your RMR is going to increase. And that makes sense because fat-free mass is metabolic tissue. So bones, muscles, organs, brain, all those tissues are metabolic tissues, and they require the input of energy to maintain their lifestyle, to maintain their lifespan. Meanwhile, fat tissue is very low metabolically. You need very, very little energy input to maintain those living cells. As well as on the right here, we see RMR begins to decline with age. And so you can go, you can have as much as a 25 to 35% decrease in your RMR as you age throughout your lifespan. Again, we're seeing here skeletal mass accounts for 20 to 25% of your RMR. So if you can increase skeletal muscle mass by 10%, you can see as much of a 2.5, 3% jump in your RMR. And while that doesn't sound like a lot, if you think about it, most people's RMR is somewhere around the 2,000-ish area. And if you increase that by 3%, that's actually a pretty big jump in calories. So just increasing your skeletal muscle mass, 5-10%, which is actually a pretty arduous task. But if you can increase it, you can massively increase your RMR, as well as just the basic activity that you need to get there is going to be increasing your energy expenditure. So 1 kilogram of muscle burns about 13 kilocalories per day. And so the more muscle you put on, obviously, the more kilocalories you are going to burn per day. So here we're looking at total energy expenditure over a lifetime. And what you're seeing here really is that, first of all, you see a kind of peak in your 20s for your total energy expenditure as it drops throughout your lifespan, as well as that kind of models fat-free mass as well. So we see here in adults, we see this increase in fat-free mass and then a drop over time. These things all kind of model together. As your fat-free mass increases, your RMR, total energy expenditure, usually increases. And then as it begins to drop with age, they all begin to drop together. Looking at this here, we see in pregnancy, we see there's differences in just your total energy expenditure depending on the trimester you are in. And now they're not large differences, but they are noticeable and they are significant differences. And some of this has to do with, obviously, as a woman goes through her pregnancy during different trimesters, there's different stages of growth that require different levels of energy for the baby, as well as you think, okay, so as the baby gets larger, it must require more and more energy. And so you look at this and you go, okay, you see it's a little bit higher here, but it's really not that much higher. And we look at first and third, and it's relatively the same. And what that has to do is compensatory weight loss or compensatory metabolic rate. And so we'll talk about that a little bit more in a second here, or in a few slides here. But essentially what it is as you expend more energy in one area, your body begins to wean off or take energy expenditure from another area. Again, looking at this, we see our total energy expenditure, our basal energy expenditure. We see them pretty much track with fat-free mass as well as age. This is just kind of more showing how these things are usually in line with each other. So if we want to measure RMR, we want to look at, how do we look at this? Okay, so we have this. This is cool. Okay, we know about energy expenditure. How can we measure it? So the most direct way is direct calorimetry. So you're using insulated chamber. And so because we know the formula down here, because we know this relative formula with chemistry, we know that food plus O2 yields CO2, H2O, ATP, and heat. And so much like let's say a cookie recipe, is the analogy I use all the time for my chemistry tutor students, or my students that tutor chemistry. Just like a cookie recipe, if you put so many ingredients in, you're going to get so many cookies out, or so much of the cookie dough out. Same thing with chemistry equations. So if we know how much food we're putting in, then we know how much oxygen it requires to break down that food. And so since we know how much food we're putting in and we know how much oxygen it requires to break down that food, we know exactly how much CO2 and water is being produced, as well as we know exactly how much ATP and heat is being produced. And if we use this insulated chamber to measure how much heat is being produced, we can therefore indirectly measure the amount of energy that that is being produced by these reactions, or that are being used. And so essentially, with this indirect, or with this direct chamber here, with this insulated chamber, we can measure the amount of heat that is released, and therefore we can use it to extrapolate and figure out all these other variables. And so obviously this is for some sort of exercise bout, because they are on a treadmill here. But if you just had someone sit in a room at rest and measure the heat change of that room, you could directly measure the RMR of that individual. But this isn't very feasible because you'd have to have a perfectly insulated room. You need to take a lot of time. You need to do a lot of different things to make this perfect for you. Otherwise, you're going to have some intrinsic error. So the way that it's more commonly done is an indirect calorimetry. So this is done using a metabolic cart. Second here. This is done using a metabolic cart, just like you see here. So essentially, we have the Parvo cart here. If you've seen this before, if you've taken assessments, there is a Parvo metabolic cart sitting right in there. You hook them up to a little spaceship-looking bubble mask here. Usually when I have this assessments class, and I tell people to lay in this, everyone gets a good laugh out of it. You get to feel like Neil Armstrong or whatever for a day. You lay down in this position anywhere from 10 minutes to a half an hour. And essentially, you are utilizing, again, we remember this equation here, we are measuring the CO2 production from the individual. And so we measure the CO2 production, and we can use that to essentially estimate or extrapolate out the amount of energy that they're producing at rest. The problem with using CO2 is not all CO2 that is released by the body is due specifically to the breakdown of food. As we remember, some of the CO2 is released from the food itself. So as glucose and fats are broken down, CO2 is released that way. But also we remember that when acidosis begins to accumulate because of glycolysis, we are releasing CO2 due to the bicarbonate buffering system, as well as there's a few other modalities in which CO2 is produced in the body. And so depending on the relative levels of each of those, that may affect this indirect calorimetry. And so this is not quite as accurate, but still, since it's probably the most feasible, it is widely used as the best marker for measuring RMR. So looking at caffeine and RMR. So something I see a lot is looking at caffeine and exercise. And so yes, caffeine is useful for exercise. It can be performance augmenting. However, you usually have to have at least 3 milligrams per kilogram. So that means for myself, I weigh about 100 kilograms. I would need to drink 300 milligrams of caffeine to see any sort of real experimental increase. As well as though caffeine can increase RMR. So we can see a 7 to 13% increase in RMR, even though it may be short term. So we see here on the right here in our inactive subjects, because caffeine is more effective on them, and because their tolerance is likely lower, because their activity level is lower, they're going to see a greater thermic change or a greater effect of the caffeine than a trained individual. As well as, like I was just said, tolerance. I apologize for being confusing there. If your tolerance is higher for caffeine, you're going to see a decreased response. And this makes sense. If you are somebody who's a habitual caffeine drinker, you can drink lots and lots of caffeine a day and feel relatively no effects. Really, all you feel, people that are addicted to caffeine, is you feel the negative consequences of you not intaking caffeine. And so as you become more well trained and as you become more of a habitual caffeine drinker, you're going to see lesser responses from the caffeine. As well as something to note from this graph here is that you see the greatest spike in RMR is about 45 minutes. So that's actually too when the best performance outcomes occur. So when you intake caffeine for performance, usually you're going to see your best or your highest increases or augmentations in about that 45 to 60-minute window. And so I see a lot of people go to the gym and they begin drinking their Celsius or whatever it is right when they begin their workout, and they work out for an hour and then they leave. Really what you're doing is you are missing the peak performance time of that caffeine intake. If you were working out for an hour and you just started drinking it right when you started working out, and let's say you drink it for the first 10 minutes, you're really only getting like a 5 to 10 window at the end of your workout where you're actually seeing any sort of real augmentation to your performance from caffeine. And much like creatine, if you time caffeine correctly, it can be very, very beneficial. Like creatine, it can give you essentially a sensation of feeling more energized during your workout. And so this is also a good segue to talk about caffeine, what caffeine really does. Caffeine does not actually give you energy. What caffeine does is it's an adenosine receptor blocker. And adenosine is what makes you feel tired. So caffeine gets in there, it blocks the receptor. Therefore, you do not get the signal sent to you that you are feeling as tired, and therefore you feel less tired. That's the explain like I'm 5 way of caffeine. But essentially what it does is it just makes you feel less tired. It does not actually energize you because it is blocking the signal that is supposed to be telling you that you are tired. And so much like creatine in a way, it just makes you feel like you are more capable or more able to exercise harder, and therefore you're going to get more damage, more adaptation, and therefore more gains. Energy expenditure. This is anything beyond RMR and the thermic effect of food. So when we talk about total energy expenditure, we're talking about anything beyond RMR and thermic effect of food. So these are things that you yourself are doing, your movements, your activity that burn energy. So looking at exercise versus non-exercise, different ways you can do it. Higher intensity, as you can imagine, is going to have higher energy expenditure. So use for more energy when using larger muscles. So you are going to use more energy. That's why, let's say a leg day is generally better for, let's say, weight loss programs or weight loss programs that use resistance training generally have more leg days in them, because about 50% of the muscle mass or more than 50% of the muscle mass in your body is in your legs. And so if you want to be utilizing the most energy, you want to be utilizing the largest muscle groups. And then high intensity interval uses more than slow, steady state. And so with that, essentially what we talked about before with high intensity interval training, what you're doing is you are spending more time on task. You're spending more time doing some sort of arduous training or difficult training. And so because you were spending more time on task doing difficult training, or because the training is more high intensity in this case, you are going to be burning more calories during that bout. So there's different ways of estimating physical activity. And so with this, it's really, really hard to say for certain what these are because your movement economy needs to be taken into effect. And so we need to do a O2 data tool, or we need to do an O2 or an oxygen data analysis. So we need to look at your VO2 max and then measure your economy, as well as how hard you are actually working with your rest intervals and your intensity is going to be highly variable for these things. And so I wouldn't look at this graph and be like, oh, okay, I did a light training day. That means I burned exactly 2020 calories. I don't think you are, but this is just a frame of reference to look at it and say, okay, what is occurring on these training days? What is the increase? What are the changes? And what are the things that are going to need to be involved, or what things are important when you are actually measuring or calculating these things? And so exercise and energy expenditures. Total energy expenditure may not increase linearly with exercise and energy expenditure. So this is what we're talking about with the compensatory energy expenditure, which we'll get into a little bit more detail here. So a sedentary individual, an increase in physical activity usually results in an increase in total energy expenditure. So if you are mostly sedentary or you are not very active individual, you are going to see relatively the same increase in total energy expenditure as you increase physical exercise. However, in a highly trained individual, increase in exercise energy expenditure is going to cause compensation in other areas. And so essentially, as you begin to exercise more intensely, your resting periods are essentially going to be in a way more restful. So you are going to compensate in areas where you don't need to be expending as much energy in order to hold on to the energy that you are taking. So this makes sense in terms of our evolution as a species. So only recently in the last maybe a few hundred years, and not even everywhere in the world right now, is food in a surplus. And so back in the day when we were hunters and gatherers and we were hunting for our food or gathering berries or whatever it might be, if we were exercising more rigorously or more often, generally, obviously, you're going to have higher physical exercise energy expenditure. But usually you were doing that because you were tracking down food. And so it would make sense that the species or the tribes that survived were the tribes that would have these compensatory reactions where if they're out hunting more and more often, when they actually get to rest, they are in a more rested state, or their body adapts to be in a more rested state. And so this makes sense in terms of evolutionarily. And now we see it manifest in terms of our highly trained athletes. So those who have, or those who are habitually more highly trained or exercise more often, are going to, yes, expend more energy during their exercise, but when they are in rested periods, are going to see less energy expended in those rested periods as a compensatory reaction for all the energy that they're expending during their actual exercise. So there's less of a decreased energy expenditure during a caloric deficit. So as well as, again, going back to talking about the tribes that were hunter-gatherers, if you were starving, if you were in an energy deficit, it would make sense that your total energy expenditure is going to go down because essentially it's your body's way of limiting you from overexerting yourself. As well as sex has little to no effect on this. So the difference between this compensatory reaction is relatively the same between sexes. So as we see here, you don't need to look at the left here. Stuff isn't super important for us. But as we see on the right here, right, this is the physical activity linear model. So this would be what would likely be happening if you were a novice or a mostly sedentary individual. You have your RMR basically right here. And then as your physical activity increases, your total energy expenditure is going to increase. But for well-trained individuals, what you really see happen is you see as the physical activity increases, you see their RMR, not their RMR, but other energy expenditure potentially go down. And so I misspoke here. This isn't truly your RMR. This is RMR plus thermic effect of food and other energy expenditures. You're not going to see your RMR go down with physical activity, but you're going to see other biological processes somewhat decrease. And you're going to see the thermic effect of food somewhat decrease in order to maintain, so your total energy expenditure is not as high. And again, this is a sort of protective mechanism in your body to make sure that you are not going to go into states of starvation. So looking at the thermic effect of food, so this is where I get to talk about a lot of the misnomers and a lot of the more recent literature for exercise and energy expenditure. So we see here what this graph is really just showing you is that higher intake diets or higher intake meals are going to cause a higher thermic effect of food, which would make sense. If you're ingesting more food, it's going to take more energy to break down that food. So if you're having a one massive meal, it's going to take more energy to break down that food. And so we see here in the black, we have a high carb, low fat versus high fat, low carb diet with 1,200 calories. It's going to have a higher, 1,200 calories, excuse me. It's going to have a higher thermic effect than if you were to do just 600 calories. And so you might be looking at this and go, okay, it's really, really good for me then to have one big meal, because if I have one big meal, I'm going to burn basically 50% more calories in that one big meal than if I had two smaller meals. What you got to remember, though, is that even though you are burning more in that one big meal, what essentially you need to do is if you ate two of these 600 calorie meals, you would get this response doubled. And so reality, just like protein feeding, if you were trying to burn fat or you're trying to lose weight, if you're trying to slightly increase the thermic effect of food, you want to be spacing out your meals. And so that's why if you've ever been a gym bro, you look at a lot of well-trained individuals, you see that they're always having small meals throughout the day because it is beneficial for weight loss as well as it's beneficial for muscle protein synthesis. And so you're starting to see here, there's a little bit of a pattern between protein intake and overall food intake. And that pattern's going to get stronger throughout this lecture. So the influence of thermic effect of food on satiety. So what this is really saying here is that after 7 hours, high protein meals were the most thermogenic, as well as strongly linked to the fullness sensation. And so what you're going to find here is that protein is actually the most filling and actually the most satiating nutrient. And so when you are trying to go through periods of weight loss, you should be increasing protein intake, mostly because it helps you with muscle protein synthesis, but also because it's going to increase the thermic effect of food. And also, if you're trying to intake less food every day, it's probably better for you to feel fuller longer from each individual meal. And so if you want to feel like that, if you want to have higher feelings of satiety from each individual meal, you want to be increasing the amount of protein in that meal. And this has to do with the fact that proteins are much more difficult to break down, as well as protein transfer across the endothelial lining of the intestines requires more energy than it does for carbohydrates or for fats. And so if we look at this here, we see a high protein meal, high fat meal, high carbohydrate meal. We see at the same time period right away, there's relatively the same amount of kilojoules burned for the thermal effect of the food. Okay, but we see over time, carbohydrate and high fats begin to drop, and that's reflected in this graph here. High carbohydrate and high fats begin to drop over time. Meanwhile, the thermic effect of protein remains much higher than the other two after a longer period of time. And so what this is saying is not only initially are high protein diets more satiating and have a higher thermic effect, but over time, protein actually kind of begins to increase or stay relatively the same. And carbohydrate meals and fat meals begin to drop. And then even 7 hours afterwards, we see that protein meals are much, much higher for a thermic effect, almost 2 to 3 times as much as carbohydrate and high fat meals. So again, leading you into the fact that the best way for you to feel full and to eat less during some sort of diet is to have high protein diets. So the basics. So the nice meme on the side here, I'm not saying it's math, but it's math. That's all it is. If you are burning more calories, if you have more calories out, if you have a higher energy usage than you have intake, you're going to be in caloric deficit and you are going to see weight loss. I use this analogy all the time. It is all about caloric restriction. Let's say that you want to burn 500 calories a day. If I gave you 2,000 calories a day in Twinkies or whatever Hostess snack you prefer, if you like cosmic brownies, I think are overrated. If you like Swiss rolls, if you like zebra cakes, if you like the honey buns, whatever they might be. I myself am a big fan of the honey buns and the Nutty Buddies. But let's say I gave you 2,000 calories of Twinkies. If you burn that day 2,500 calories with your RMR, with your total energy expenditure, with your thermic effect of food. If you burn 2,500 calories in that day, you are going to lose 500 calories worth of stored energy or stored fat. Now, keeping in mind, let's say during that analogy, I gave you a pill for all your other micronutrients, and you ignored the fact that Twinkies will probably make you feel lethargic, and therefore you're not going to be moving as much. But the math remains the same. If you are burning more energy than you are taking in, you are going to lose fat. It's as simple as that. Specifically for protein, as we saw back here, if you are intaking protein calories, the amount of energy to break down those protein calories is going to cause a higher thermic effect of food and cause even more of a deficit. So in this way, really the baseline is fats and carbohydrates. And then if you can be intaking more protein, you're going to see even greater deficits because yes, protein accounts for 4 calories per gram, but breaking down that protein to get those 4 calories per gram takes more energy. And therefore, essentially, you could think about it as protein is a little bit less calories per gram and therefore is better for weight loss. And then finally, we see here, if your calorie intake is higher than your calories out, you're going to have a weight gain. This is essentially calculating the ideal body weight for a model. So if you want to look at this, I'm not going to go over this. If you want to look at what the percentage is, how you want to lose weight, you can use this graph to kind of estimate that, as well as you can just do the math yourself. So why is body composition important? And so we see the extreme example here, that obviously the individual on the left here, the man shaped like a dinosaur, whatever he's shaped like, is 200 pounds, 30 years old. But the man on the right, who is extremely fit and is popping veins everywhere, is 30 years old and also 200 pounds. But they're not the same individual, and they're not going to have the same RMR. And as you can imagine, as you've been listening so far, the individual on the right is obviously going to have higher free fat mass and therefore likely have higher RMR. And so with this, we're going to talk about essential and non-essential body fat. And so essential body fat is needed for normal physiological function. So this is found in your muscle cells, your nerve cells, your bone, your intestines, your heart, your liver. If you've ever seen a cadaver, when you open up the GI, when you open up the abdomen and the thorax, you see a lot of stored fat. And fat is used as an insulator and a cushion. And it makes sense if you have a lot of very important organs in your thorax and in your abdomen, you want to make sure that they're well protected from outside dangers. And so you have a lot of fat protection in those. So for males, lucky us, our essential fat is about 3 to 5% versus females is about 8 to 12%. And so naturally, when you look at body fat percentage in women, it's going to be much, much higher because you guys have a much higher level of essential fats. And this is for the variety of internal organs that you have specifically for childbirth. You need to make sure, or the body makes sure, that it is prepared at any point for the fertilization of an egg. And as women are obviously more aware of than men, every month you have your menstrual cycle. And the reason that you're having that menstrual cycle is because the default state of the female species within the mammalian family is the preparation for pregnancy. Every single month for humans, or for most female humans, they go through the menstrual cycle because the body is essentially preparing to be pregnant. And then when it finds out that it's not pregnant, it has some sort of compensatory reaction. And so because of that, the female body naturally stores more fat or requires more essential body fat than the male body, as well as we're going to look at the difference between visceral and subcutaneous fat. So visceral fat is around your organs. This is what I was talking about in the abdomen and thorax, surrounding the heart, the GI tract, liver, all those things. And then subcutaneous fat, cutaneous meaning skin, is just beneath the skin. And so looking at adiposity, looking at obese individuals and their differences in their fat cells, is essentially obese individuals have not only more fat cells, but their fat cells are also larger. But as we've learned, is individuals that grow more fat cells can never get rid of them. What you're seeing here is that for a never obese individual, you have, let's say, an X amount of fat cells. Say you have whatever, there's 15 fat cells in this little clump here. Obese individuals not only have more fat cells, but they also have larger fat cells. And then if you were obese and you became non-obese, or you went through a period of weight loss, you can never really get rid of those fat cells, but you can shrink them in size. And so over time, all you can really do once you have grown these fat cells is begin to shrink them. That's why for individuals, it's one of the potential mechanisms for individuals that were obese why it is much more likely for them to slip back into obesity, and why it is technically or sometimes harder for them to get or why sometimes it's harder for them to lose that weight. We'll also talk about ghrelin. We'll talk about ghrelin here in a second. Yep, we'll talk about ghrelin here and leptin in a second. So we have different types of adipose tissue. So one of the things we're going to talk about is brown fat. So brown fat is more prevalent in hibernating species like the bear, as well as in babies or infants of the mammalian species. And so brown fat has a higher mitochondrial supply, therefore being more metabolically active. So it produces heat at rest. And so this is good for hibernation of certain species, as well as for infants, because infants are much smaller and they're not as capable of producing heat. That's why infants need to be swaddled, why they're held close to their mother or their father, why they are generally dressed much warmer than adults are for the same temperature. They also utilize fatty acids for energy. So they are, again, they're burning more energy. And so your brown fat here is going to be more metabolically active than your white fat cells. So brown adipose tissue, so it's present in adults, but the extent is not clear. And so this is mostly activated by cold exposure, and that would make sense since it is metabolically active and it produces heat. It would make sure that you need some, or it makes sense that you need some sort of stimulus like cold exposure to make sure that you are to ensure that you are activating these fat cells. Prevalence estimates range from 3 to 50%. So you're going to see these change in different species or different portions of our species. So individuals that are tribes along the equator are going to have much lower predisposition for brown adipose tissue than individuals, let's say, that have lived in the northern Siberian continent or have lived in Northern America. These individuals that are used to being around cold are going to have a higher prevalence of brown adipose tissue, as well as it tends to be more prevalent in females and younger, healthy individuals. So weight loss is multifaceted. There's no one solution for everyone. And so this is one of those things that we see everybody sees in the social environment today, is that there's always like, oh, this quick weight loss pill or get skinny quick. Really, the truth is, and what the sad truth is that the best way to lose weight is to work hard and be disciplined. It's the only way that works. These pills that offer to boost your metabolism, or they offer to do this and that, most of them aren't true at all, as well as they have some sort of misnomer to them that isn't essentially true. But it can be easier or it can be more difficult for certain people depending on their genes. So this one allele associated with obesity, essentially what it does is it decreases your satiation. So with each meal, you feel less full, and therefore it's going to likely increase your caloric intake. And so for those individuals, it takes more self-control to not eat as much food. Now, this isn't a get out of jail free card for those individuals. A lot of people have this gene and still are able to go through periods of weight loss and maintain relative body weight. But this is one gene that may be a precursor to obesity, as well as individuals that release more ghrelin or release less cholecystokinin are going to feel more hungry. So if you're releasing more of the hunger hormone, or if you're releasing less of the full or satiating hormone, or you're releasing more leptin over time, you're going to see changes in the way that these individuals intake food. More than likely, they're going to be taking more food in, and therefore they're going to need to work harder. They're going to need to work harder to maintain or to lose weight. And so there is predisposition to obesity, but as you can see, the American population versus many other populations, it has a lot more to do with lifestyle than it does with genetics. So which is better for keeping muscle mass and burning fat? So what we've learned so far from our training for strength, or training for hypertrophy, for our training for fat or weight loss here, looking at these, which one do we think would be better for keeping muscle mass but burning fat? And so we see here on the bottom, I lost my cursor, we have the same exact caloric deficit. We have the same exact caloric deficit. So you'd think, well, we should be learning, or we should be losing the same amount of fat. And that's true. That's true. You would be losing the same amount of fat in a short period of time. But what's likely occurring is, because you are adding exercise, you are likely increasing free fat mass, or lean mass. So if you're increasing free fat mass, you're increasing lean mass, what's happening to your RMR? well, your RMR is likely then going up. And if your RMR is going up, what else is likely to go up? Your total energy expenditure. And we remember that there's a compensatory reaction, so that's not exactly linear, but for the most part, unless you were an elite trained athlete or you were highly active, increases in your RMR are going to cause increases in your total energy expenditure. Specifically because if RMR is going up, you're likely not changing the amount of exercise that you're doing. And so therefore, those two are combining to cause an increase in your total energy expenditure. Looking at RMR and caloric restriction. So what we see here is when you are doing certain activities and doing certain types of weight loss things, it can negatively or positively affect your RMR. And so for control here, we see that an expected RMR for our control is relatively the same as the observed RMR. But we see in caloric restriction alone, their expected RMR is about 90 calories different than their actual observed RMR. And then we see here in caloric restriction and exercise, we see their expected RMR is again about 90 calories different than their actual RMR. And so we're seeing here realistically, I don't know why they kept dragging. We're seeing here is that individuals that go through different levels of exercise or different levels of diet are going to have relatively similar outcomes, whether you're doing caloric restriction, whether you're doing caloric restriction and exercise. Essentially, the effect on your RMR due specifically to the caloric restriction or due specifically to the caloric restriction exercise is not very different. But remember, if you are exercising, that means that you are putting on if you're putting on free fat mass, which is going to cause this expected RMR to go up because we're measuring it based on skeletal muscle mass, as well as your actual observed RMR is going to go up. Because if you are increasing skeletal muscle mass, it means you're increasing metabolic tissue, and therefore you are increasing the amount of energy you're going to be burning at any one period of time. So you guys have probably seen this before, the female athlete triad. And so, much like everything else in biology, weight loss, muscle gain, bone gain, all these things are specifically built primarily for the male body. Women have to go through a much more arduous task to get the same gains, to get the same increases in performance that men do. And so when you see female athletes increase 10% comparatively to men increasing 10%, you know that that female athlete was probably working harder to increase it 10%. They probably had to be more disciplined in their nutrition, more disciplined in their exercise, and overall probably had a more difficult time seeing those increases as their male counterparts would. So Mythbusters, we're gonna talk about some Mythbusters here. Good old fashioned show. We'll get into it right away here. So fat burning zone. So misconception, keeping your heart rate in the fat burning zone results in greater weight loss. No, it just results in greater fat burn. But as we remember, if you are burning more fats at a certain intensity, it means you're probably utilizing less carbohydrates at a certain intensity. So this is probably a very, very low intensity. There is an optimal range where you are going to be burning the most carbohydrates and the most fats for long duration exercise, but it is not within the fat burning zone. So the recommendation really is just to work hard. Total calorie expenditure, not heart rate, is what matters the most. So doing whatever exercise you can that allows you to burn the most energy is what's going to cause the most weight loss, not actually exercising in the fat burning zone. Because yes, more than likely you are in some sort of state, let's say where your RMR is set and you are at, 83% fat burn compared to 17% carbohydrate burn, but the amount of energy that you are still utilizing is just going to be the same. You need to make sure that when you are exercising, you are worrying more about total energy expenditure during the exercise rather than what burning zone you are in. Daily weight changes is something we talk about all the time. So 1 pound of fat is about 3,500 kilocalories. So if you wanted to lose 1 pound of fat per week, you would need to lose 500 calories or be in deficit 500 calories each and every day. And so when I went through this is where I'll talk about myself a little bit here. When I went through my little cutting phase that I wanted to do was experiment on myself. I wanted to get myself from about 10.5% body fat down to 7.5% body fat. Realistically, what I was doing is I was planning my nutrition around this paradigm here, the 3,500 calories per pound of fat. I wanted to be cutting about 8 pounds of fat, and I wanted to do it in about 3 months. So it's relatively easy. 8 pounds of fat in 3 months. That means I have to do a little bit less than a pound per week. When what I really did is I took a high protein diet. My diet was consisting about 55 to 60% protein, for my calorie intake. But what we would see, or what I would see, is that as I was doing my body composition on a biodex, a biological impedance analysis, is that you're going to see massive variations day to day. And so I hear a lot of people, even people within my department, will be like, "Oh yeah, I'm trying to lose weight," but I'm up a pound from yesterday. That happens. Most of your daily change in weight has to do with fluid retention, activity, sleep, hormones, but mostly fluid retention and carbohydrate retention. And so this is going in line with creatine. We hear a lot of times when you take creatine, you get bloated. Realistically, when you have high carbohydrate intake is when you're going to actually gain the most weight, because for every 1 gram of carbohydrates, every 1 gram of glycogen that you store in your muscle, you need to store 1 gram of water, or excuse me, you need to store 4 grams of water. So 1 gram of carbohydrates means 1 gram of glycogen means 4 grams of water. And so if you are in a very rested state where you have high muscle glycogen, you're going to have more intramuscular water, and therefore you're going to weigh a little bit more. So water affects you in 2 ways. So just general hydration. If you are more hydrated, you're going to weigh more. But also, if you are in a if you're in a rested state and you have high and adequate nutrition, and that means you have high levels of intramuscular glycogen, you're going to be retaining that weight. And so let's say after some sort of high intensity couple of days of exercise, you really haven't been supplementing with carbohydrates like you're supposed to, so you've been dropping your intramuscular stores of carbohydrates, as well as you've not been hydrating as much, you might see as much as a 3, 4, 5 pound drop right away in your weight. And this is kind of what people that are wrestlers are familiar with. So if you're a wrestler, I have a couple of good friends that are wrestlers, and I've asked them before. I said, if you had a performance, let's say it's Monday, and I said you have a meet this Saturday, how much weight could you realistically cut in those 6 days? And usually the answer I get is about 10 to 15 pounds. That is all fluid. You are maybe getting yourself in deficit, maybe 4,000 or 5,000 calories. So maybe you're losing a pound and a half of that from actual fat loss. But the most part you're realistically losing is through hydration, through glycogen loss, through substrate depletion, through the efflux of certain electrolytes in from your body, right? Realistically, that is a short-term weight loss change. So when I was doing my bioelectrical impedance analysis, which is a way of measuring body composition, I would find that there was a night I had gone out drinking and I went in the next morning to go work out. And so I had worked out really, really hard on the Friday because I knew that I was going to go out to celebrate with some of my friends. And then I came in the morning. And so obviously I was dehydrated, but also my nutrition after that workout was really, really poor. So I had readily depleted most of my muscle glycogen because I'd done a very, very difficult workout. And when I came in the next morning and put myself on the analysis, it told me that my body fat percentage was about 4.9%. When in reality, when I came back and I did it at the correct time, it was about 8.1%. And so the apparatus thought that I had just lost 4 pounds of body fat, or measured that I lost 4 pounds of body fat essentially overnight, when in reality, it all had to do with my hydration status. And so as you are going through your weight loss journeys, or as you're trying to gain weight, lose weight, you should really be measuring these things more on a week span or even on a 2 to 3 week span. So you shouldn't be looking at it and be like, oh, I went up a pound today, so that means whatever I did today is something that I should not be doing. What you really should be doing is tracking it week to week. Measure on a Sunday, put yourself at the exact same hydration, eat the exact same thing the night before, do the exact same activity, whatever, within the last 48 hours. Make sure everything stays relatively the same before you do your weigh-ins or before you do your body comps, to ensure that your measurement is the most accurate. And then track that week to week rather than day by day or hour by hour. So looking at this, when caloric restriction and caloric expenditure are similar, you see similar weight loss. So when you have, when you are constraining, right, you're constraining your caloric intake and you are combining it with exercise, you see here you're going to have a greater change in weight. And so that makes sense. If you are expending more energy, if you are eating less energy and going through some sort of moderate workout, you're going to see a greater energy expenditure and therefore a greater weight loss. And so we see here, right, our controls are staying relatively the same. Our controls plus exercise plus our controls are relatively tracking in the same manner. And so with diet plus exercise, you're going to see greater increases, or likely greater increases than just diet alone. However, it is not always the case. And so you want to increase your energy expenditure via exercise, but also a very, very important part of it is your diet. Essentially, that's what this whole lecture is about, is yes, exercise is very important, but diet and energy intake is also very important, as well as the reason that these are not significantly different here. You're saying, okay, Trevor, this is confusing. You're saying that exercise and diet are important, but here they look like they're pretty much the same, or exercise is even a little bit worse. And then here, that exercise looks a little bit better, but it's not significantly different. So what really is happening is, yes, between diet and exercise, the initial change is not much, but we have to remember that with diet and exercise, you are also increasing fat-free mass. And so your weight loss is not going to be as intense as if you were just doing caloric restriction. Because if you were increasing fat-free mass, your overall weight should be increasing. So in reality, what is occurring here is this is probably decreasing your fat mass more intensely. So you're seeing greater decreases in your fat mass, but because you are adding free fat mass, you are not seeing the exact same, or not seeing bigger changes in weight loss. And so this is mostly to be thought of as if you were doing extreme resistance training. And so this is something I hear a lot when I talk to specifically women within the profession, women that are not within the profession. They do a lot of cardio, and I'll talk to them. I'll try to teach, and I'll say, why don't you ever do resistance training? And they'll be like, well, I don't want to get too big. I've heard that a lot. I've even heard men say that. I don't want to get too big. Which my response is I have been weightlifting since I was 16 years old. I have been trying to get too big for 10 years, and I am not too big yet. So you're not going to accidentally get too big by resistance training, okay? It's going to take a lot of work for you to get too big. But resistance training mixed with cardio is really important, because that cardio gives you that energy expenditure right away. But that resistance training also gives you free fat mass, or fat-free mass gains over time, which is going to lead to a higher RMR. And therefore, essentially, your workouts will not need to be as intense to see the same weight loss over time. As well as we'll look at fasted exercise, essentially low carbohydrate, high fat. So this is going to lead to increased fat utilization. That would make sense. So increased fat utilization because you have high fat diets. But if you remember, when you are utilizing fats, what's happening to the rate of ATP production? Well, it is going down. And so these low carbohydrate, high fat athletes were actually slower by 3.4%. So again, just because you are utilizing more fat does not mean that you are burning more fat. And specifically for performance, you do not want to be burning more fat, because you want to be utilizing the carbohydrates, because that allows for quicker ATP. Quicker ATP means more force production and availability of ATP for your muscles, which means a higher performance. So in essence, don't look at these things in one paradigm or through one lens. You want to make sure what is going on with all these things. And so in essence, you want to make sure that you are balancing your diet correctly and using carbohydrates. You want to use carbohydrates to fuel exercise. Carbohydrate and protein diets do not lead to weight gain if you are in caloric deficit. Again, I talked about this before, the amount of individuals I know that are going through weight loss periods, guys that are trying to train for bodybuilding, and they'll say, oh, I'm cutting out carbs. No, stop cutting out carbs. There's so much literature, there's so much research that is telling you that you need to have high carbohydrate, high protein diet in order to stimulate muscle protein synthesis, and high carbohydrates in order to replenish those stores of muscle glycogen, so that you can begin to work out it more intensely. So high protein, high carbohydrate diets can lead to higher intensity and therefore greater caloric expenditure. Carbohydrates and protein likely are better than just carbohydrates alone, because protein leads to muscle protein synthesis. So again, I know I'm beating this dead horse here, but I've heard this so many times, it drives me absolutely insane. And this is one of those things that I don't like to talk about, because when I walk around telling people, hey, your diet should be mostly carbs and protein, they're, oh, that's a gym bro attitude. You should be having lots of protein. You should just be having lots of carbs and protein in general in your daily diet. That's why you're seeing massive changes in the food pyramids, because no one can agree, because you have the nutritionists that are like, oh, you don't need that much protein. And then you have the exercising industry, you have the general health industry that is like, well, protein has all these benefits and it has very little of these negative outcomes that high fat diets do. So why are we not increasing protein? So this is kind of the war that's been waging within the literature, not even within the literature, within social media, because the literature is overwhelmingly saying high carbohydrates, high proteins are good for performance, they're good for weight loss, and they're good for just general activity or general activities of daily living. So in summary, I know I was a little bit all over for this lecture. It's very early in the morning, so I did my best here. Hopefully you guys are still following along in your understanding, as well as hopefully you guys retain some of this information about weight loss and caloric intake and how you should utilize these things for caloric deficits. And so our energy expenditure is based on resting metabolic rate, physical activity, and thermic effect of food. So these three things in tandem. If you can increase your RMR by strength training, resistance training, you can increase your energy expenditure. If you can increase the thermic effect of foods, the amount of food or the amount of calories you're utilizing to break down your food by, let's say, increasing your protein intake, you can increase energy expenditure. And you can increase energy expenditure by increasing physical activity. But remember that if you increase physical activity very habitually, you're going to see compensatory reactions in other areas. Not saying that physical activity is bad for energy expenditure, just saying that over time, the linear relationship begins to become skewed and you're not going to see the gains that you would see over time. Same with like strength gains, right? You see that diminishing return. As you increase energy expenditure, as you increase strength training, you're going to get big changes right away. And then over time, they're going to begin to peter out and kind of plateau. Again, physical activity is still really important for health and still really important for weight loss. It just isn't as useful when you're highly trained compared to when you are novice trained. So RMR is affected by many factors like weight, sex, age, body composition. RMR will decrease with weight loss, assuming you are losing metabolic tissue. If you are maintaining metabolic tissue, you are maintaining muscle mass while losing weight, which is rather difficult, your RMR will stay the same. That's why you see people that are going through a bulk cycle and then a cut cycle. You bulk so that you can get that muscle mass, and then you cut so that you can try to maintain the muscle mass while you wean off the fat. It is very, very difficult to gain muscle mass while you are in caloric deficit. And this is something that I found as well when I was doing my cutting cycle, is that I lost about 8 pounds, but about a pound to a pound and a half of it was muscle mass. Because when you are in a caloric restriction like that, it is almost impossible to maintain muscle mass. Now, with my high protein diet, if I had been eating a low protein diet, I probably would have seen greater decreases in muscle mass. As well, if I had not been working out, I've seen greater decreases in muscle mass. And so it's one of those things I look at and I go, okay, how can I modulate that? And I've read some literature recently that kind of told me what I was doing wrong and why my muscle mass increased by a pound. Essentially, I should have been able to lose about 10 pounds and lose only about a pound of muscle mass. So I was close, but not quite perfect. Weight loss or gain is all about energy deficit or energy surplus. It's important to maintain healthy body weight throughout the entire lifespan. Remember, with our fat cells, we want to make sure that we are maintaining a healthy body weight. If you lose yourself for a few years or for a decade, that can have long-term ramifications onto your life. Essential versus non-essential fat and brown versus white fat. Obviously, we want that essential fat, and then we want that brown fat if we can. For females specifically for essential body fat, if you are not maintaining levels of essential body fat, I had a friend who was a pretty premier track athlete. She was a sprinter at University of North Dakota, won a couple conference titles. Her body fat was about 8%, which is too low for most women. And so she was started having a lot of health issues. She started becoming amenorrheic. She started having bone deterioration. She started getting kidney problems because her body fat was so low when she was exercising at high capacity, it was starting to become detrimental to her body. So there are many myths around weight loss. This is one of those chapters that I really, really hope and really, really expect that I get a lot of questions about, because when I talk to individuals that are fourth year kinesiology students, even when I talk to people that are master students or people that are in the PhD program with me, there's a lot of misnomers. And I'm sure even something I said today probably isn't totally accurate. Maybe I understand something not quite as correct as it should be, but there is a lot of extremely false information propagated out in social media, specifically because people want to make a quick buck. Nobody wants to be told that if you want to lose weight, you have to be disciplined and work really hard. They want to be told, okay, if you take this pill and if you do this, you can lose weight really, really fast. So the social media around weight loss and around exercise and energy expenditure is very, very skewed, because people who push it to gain money are not the people who are actually doing the research and trying to understand what is occurring. Daily changes are not related to weight loss, weight gain. Remember that your daily changes in weight have more to do with your hydration status and your overall macronutrient intake, as well as your glycogen storage within your muscle. And then weight loss can be complicated, so take an individualized approach. So again, this is saying you can look at these general models and say, okay, what's good? What are the general things that I should be doing? What are the overall good health ideas that I should be following? But for individuals, it's going to be different. So just because it worked for someone else doesn't necessarily mean that it worked for you. And just because it didn't work for someone else doesn't mean that it's not going to work for you. So you want to be essentially experiment with these things over time, like I did with myself. It was the first time that I'd really gotten down to counting every single macro. I've been looking at what my energy expenditure was, looking at the different things that I was doing, and I wasn't even doing it that intensely. But even with a good amount of time being put into it, I still was not doing it perfect. And so if you want to really optimize these things, I urge you and encourage you to look at the literature, look at the different things, and then try different things. See what seems to work best for you, but make sure you're doing it over a long period of time and not on a daily basis. So that pretty much ends our lecture here. Again, I apologize if I was a little all over the place today, early in the morning. But for the most part, make sure that if you have any questions on this, or you have some sort of argument, or you have something that you want to talk about with this, please, please, please reach out to me. This is our third to last lecture, I believe. We have one more lecture on the environment, and then I'm gonna have another lecture on muscle building and muscle healing, which will all be on exam 2. And so that pretty much sums up the lecture today. If you guys enjoyed it, I'll see you next time.